2005 Grade 11 Hypatia Math Contest. Question number 1. For numbers A and B, the notation A star B means A squared minus 4B. For example, 5 star 3 means 5 squared minus 4 times 3, which is 13. Evaluate 2 star 3. So according to this definition, it would be 2 squared minus 4 times 3, which is 4 minus 12, which is negative 8. Part B. Find all values of k so that k star 2 is equal to 2 star k. So I think we'll have an equation here. So the first part is k squared minus 4 times 2. And then this part is 2 squared minus 4 times k. So solving, we get k squared minus 8 is equal to 4 minus 4k. Let's put everything on one side. And we get k squared plus 4k minus 12 is equal to 0. And I'm pretty sure this factors really nicely. K, 6, 2, plus minus? Yeah. So that means k is either negative 6 or positive 2. Part C. The numbers x and y are such that 3 star x is y and 2 star y is 8x. Determine the values of x and y. So this first guy would be equivalent to 3 squared minus 4x is equal to y. And that one would be the equivalent of 2 squared minus 4y is equal to 8x. Right? So I guess we just have a system of equations here. So this is 9 minus 4x is equal to y. So we'll substitute that into there. So we get 4 minus 4y, but y is 9 minus 4x is equal to 8x. And then we just solve this. So this is going to be 4 minus 36 plus 16x is equal to 8x. So 8x is equal to, what is that, minus 32, I think. So therefore x is equal to, plus 32, because it would be minus 32 on that side. And then when I brought it over, it would be plus 32. So x is going to be 4. And then to get the value of y, substitute it into there. So y will be 9 minus 4x. So y is going to be 9 minus 16. So y is equal to negative 7. And there you go. Number 2. Gwen and Chris are playing a game. They begin with a pile of toothpicks. Use the following rules. 2 players alternate turns. On any turn, the player can remove 1, 2, 3, 4, or 5 toothpicks. The same number of toothpicks cannot be removed on 2 different turns. The last person who is able to play wins, regardless of whether there are any toothpicks remaining in the pile. For example, if the game begins with 8 toothpicks, the following moves could occur. Gwen removes 1 toothpick, leaving 7 in the pile. Chris removes 4, leaving 3 in the pile. Gwen removes 2, leaving 1 in the pile. Gwen is now the winner since Chris cannot remove 1 because Gwen already removed 1 on one of her previous turns. And the third rule says that 1 toothpick cannot be removed on another turn. All right. So number 1, suppose that the game begins with 11 toothpicks. Gwen begins by removing 3 toothpicks. Chris follows by removing 1. Then Gwen removes 4. Explain how Chris can win the game. So I don't think there's anything too complicated here. We've got Gwen and Chris. So we started off with 11, right? So we'll just put remaining here. So when the game first starts, there's 11. Gwen removes 3. So then there's 8 left. Then Chris removes 1. So then there's 7 left. And then Gwen removes 4. So then there's 3 left. So they're saying, how can Chris win? Well, at this point, if Chris removes 2, then there'd be 1 left. But then you say, well, okay, well, Gwen can remove that last one. She can't because Chris already removed 1. And the rule states that if a number of toothpicks has been removed, that same number cannot be removed again. So Gwen cannot remove 1, so she has no choice. She has no play. So since Chris has the last play, he wins. So you can just write it out in Word. Chris chooses to remove 2 toothpicks. And then explain in words exactly what I explained, that Gwen does not have a move since she could only move this last one, but she's not allowed to remove one because Chris already removed one. And the same number of toothpicks cannot be removed on 2 different turns. All right, part B. So probably pretty similar. Suppose the game begins with 10. Gwen removes 5. Explain why Gwen can always win. Okay, so again, Gwen, Chris, and remaining. So let's see what we get. So we first started off, how many? 10 this time, right? Okay, so then Gwen removes 5, so then there's 5 remaining. Okay, so then now what can Chris do? If Chris removes, let's say, well, Chris cannot remove 5 because 5 has already been done once. So once it's been done once, it cannot be done again. So Chris could remove 1 toothpick. That's possible. And then there would be 4 remaining. And then Gwen can remove all 4. And then she would win. Okay. Another scenario is Chris could remove 2. And then there would be 3 left. And then Gwen could just remove those 3. And then there'd be 0 remaining. Another scenario is that Chris could remove 3. And then there would be 2 left. And then Gwen could remove those 2. And there'd be 0 remaining. And Gwen would win again. And the final scenario is Chris could remove 4. If he does, there's 1 remaining. The Gwen could remove that 1, and then there'd be 0 left. So no matter what Chris does, Gwen can find a way to win the game as described. And finally, C. C says that suppose the game begins with 9 toothpicks. Gwen begins by removing 2. Explain how Gwen can always win. Okay, so same thing here. Let's see here. So we're starting this time with 9. And then Gwen removes 2. So we have 7. Okay, so then we got to figure out, no matter what Chris does, Gwen can always win. Okay, so let's say Chris removes 1 toothpick. There's 6 remaining. And then the maximum that Gwen could remove is 5. And then if she does that, there'd be 1 remaining. But Chris cannot remove that last one because he's already removed 1. So he cannot remove 1 again because of that rule. So that means Gwen wins. Okay, great. What if Chris removed 2? But he can't because Gwen has already removed 2. So he cannot remove the same number because of that rule. So he can't remove 2, so he can remove 3. If he does, there would be 4 remaining. And then Gwen can just remove all 4, and if she does, there'd be 0. So she wins that way. What if Chris removes 4? If he does, then there would be 3 remaining, and I think Gwen can just remove all 3, and there'd be 0. And then finally, if Chris removes 5, which he can, there'd be 2 remaining. Now, Gwen cannot remove those 2 because, remember, she's already removed 2 previously. But she could remove 1. And if that's the case, there'd be 1 remaining. But Gwen wins here because Chris cannot remove that 1. Because Gwen has already removed 1. So he cannot remove the same number. So in that case, Gwen wins again. So as you can see, then you can write this out in words. No matter what Chris does, Gwen can always figure out a way of winning the game. In the diagram, triangle ABC is equilateral with a side length of 4. Points P, Q, R are chosen on sides A, B, BC, and CA, respectively, such that AP is equal to BQ is equal to CR is equal to 1. Okay, determine the exact area of triangle ABC. Well, triangle ABC is, as they have mentioned, an equilateral triangle. And when you draw a perpendicular like that, it cuts that side into two equal halves. So if the full side length was 4, as they mentioned, this would be now 2 and 2. This side length is 4, so we can call that perpendicular x and then use Pythagorean theorem to figure out x. X squared plus 2 squared is 4 squared, so x squared would be 16 minus 4, so x is going to be root 12. So the area is 1/2 base times height. The base is 4, the height is root 12, so that's 2 root 12, and root 12 is what? 2 root 3, so that's going to be 4 root 3. Now, some of you remember a formula for the area of an equilateral triangle, and if you do, I think that will help. That formula is that the area of an equilateral triangle is equal to root 3 over 4 times s squared, where s is the side length. In this case, the side length is 4, so it would be just root 3 over 4 times 4 squared, which is just 4 root 3. So as you can see, we got the same answer, but this way is a little bit faster. So that takes care of part A. Part B, determine the exact areas of triangle PQB, PBQ, and PQR. Explain how you got your answers. Okay. All right. Well, PQR. Let's start with that one. This one, PQR. That one is equilateral, right? Because of the symmetry of this diagram. Because if you were to label this, this is going to be 1, 1, and 1. Therefore, those are going to be 3, 3, and 3. So because of the symmetry here, these are going to have all three same sides. And then these angles are 60 because it's equilateral. The big one, they even tell you that. ABC is equilateral. So I guess you can use cosine law, right? And this is a grade 11 test, so you guys definitely would have learned cosine law. So let's use cosine law on any of these triangles. Let's just use it on this one here, PAR. And the side length, I will just call y from P to R. So using the cosine law, it would be that y squared is equal to 1 squared plus 3 squared minus 2 times 1 times 3, and then the cos of 60. So that means y squared is equal to 1 plus 9 minus 6, and the cos of 60 is a half, so y squared will be 10 minus 3, which is 7. So y is root 7. And then since PQR is equilateral, we can just use that formula to figure out the area. The area would be therefore just root 3 over 4 times s squared. S in this case is root 7. So that's going to be 7 root 3 over 4. Yeah. Okay, so that took care of that one. Now we just have to do PBQ. PBQ. All right. How do I do PBQ? Okay, I think that's fairly easy. Triangle PBQ is going to be the big triangle, ABC, minus the one we just figured out, which was triangle PQR. And then you have to divide by 3, right? Because PBQ is just one of those three guys. Yeah, and they're all equal. I got it. Okay, so that should be easy. We already did this. ABC is 4 root 3. PQR we got as 7 root 3 over 4. And then we have to divide by 3. And when you crunch out these numbers, you get 3 root 3 over 4. And that completes number 3. An arrangement of a set is an ordering of all of the numbers in the set, in which each number appears exactly once. For example, 312 and 231 are two of the possible arrangements of 1, 2, 3. Determine the number of triples, ABC, where ABC are three different numbers from the chosen set 1, 2, 3, 4, 5, where A is less than B and B is greater than C. Explain how you got your answer. All right, so they've given us some parameters here that B is greater than A, and B is also greater than C. Okay. All right. Now, I have a choice here. I can list them all out, which I could, or I can do it quickly. I prefer to do it quickly, but I will need to explain how. So here's a set. So the first thing we need to do is from that set of 5, we need to choose 3 numbers, right? 1 for A, 1 for B, and 1 for C. So from 10, choose 3. And 10 choose 3 is 10 factorial over 10 minus 3 factorial times 3 factorial. And when you crunch out these numbers, oh, sorry, it should be 5. Sorry about that. Some of you are probably wondering, why is he using 10? Okay, no problem. So from 5, choose 3. All right, well, that makes it easier, a little bit easier of a calculation. 5 minus 3 times 3 factorial. So that means this is going to be 10. So from these 5 numbers, I have to choose 3. And there's 10 different ways of doing that. Okay. Now, the arrangement is this inequality that when we have these numbers, the B is going to be bigger and the A and C have to be smaller. So for example, let's say from these 5 I chose 3 numbers and I chose 1, 3, and 5. Now the B's got to be the bigger one. So the 5's got to be the B and the 1 and the 3 can be AC. But you can also have the C and the A reversed. So here's one scenario and here's 2 scenarios for every single case. So for each of these 10, you'll have 2 cases. So it's actually 10 times 2. So there's a total of 20 cases. So hopefully that made sense. I mean, and you can always list these cases manually. You can write out all 20. Wouldn't take you that long. But I think because this question is going to get bigger, as you can see, there's 6 here, and then there's 8 here. I wanted you to do it in a way that is quicker. Part B. How many arrangements of 1 through 6 contain the digits 2, 5, 4 consecutively in that order? Okay. So you're going to have an arrangement of 6, right? And you want 2, 5, 4 to appear. Right? So that means that the 2, 5, 4 can appear in several ways, but they've got to be consecutive. So it's going to be like that, or it could be like this, or I think there's only one other way, which is the last 3. Okay, so that makes sense. Now you say, well, what about the other numbers? What goes here and what goes here? What goes here? Well, we'll just call them A, B, C for now. Like that. Obviously, the other 3 numbers from this set right here. Now, this is 4 different ways of doing it. So keep that in mind. That number is going to be important, 4. But for each of these ABCs, there's 6 ways of arranging them. ABC, ACB, BAC, BCA, CAB, and CBA. Yeah. So 6. So you take this 4 and you multiply by that 6, and you get the total, which is 24. And like I said, you can always manually write these out, but it would take a little bit more longer time to do so. And now we come to letter C. And C states the following. A local peak in an arrangement occurs when there is a sequence of 3 numbers in the arrangement for which the middle number is greater than both of its neighbors. For example, the arrangement 3, 5, 2, 4, 1 of 1, 2, 3, 4, 5 contains 2 local peaks. This one, 3, 5, 2, and this one, 2, 4, 1. Determine with justification the average number of local peaks in all 4, 0, 3, 2, 0 possible arrangements of 1 through 8. All right. So let's give ourselves some room. So first, I would like to explain where did they got this from. 1, 2, 3, 4, 5, 6, 7, 8. Right? There's 8 numbers this time. So because there's 8 numbers, for the first number you have 8 choices. For the second number, you have 7 choices because they cannot be the same. It has to be different numbers. 6 choices for that number, then 5 remaining choices, then 4 remaining choices, 3, 2, 1. And then you have to multiply all these. And when you do, it's essentially just 8 factorial, right? And 8 factorial is equivalent to 4, 0, 3, 2, 0. So that's where they got that number from. Now they're saying something a little bit different. Like, what is the average number of local peaks? Okay, average number of local peaks. How would you calculate that? Well, like any average, you would calculate, first of all, the total number of peaks that would occur, and you divide it by the total number of arrangements. So that would be the calculation. Now, the total number of arrangements, they've already given you. It's this number right here. So 40320. So all we have to do is figure out the total number of peaks, and then we'd be done with the question. So here we go. Now, the good news here is that part A and part B that I had just explained, that system will be used again. So let's talk about how that system will be used. So the first thing, of course, is very similar to part A. We have now 8 numbers. So from those 8 numbers, I want to choose 3. All right. And very similarly, it's going to be, what, 8 factorial, 8 minus 3 factorial times 3 factorial, and that's 56. Okay, so that's pretty easy, right? But remember, if I have, let's say, let's just choose 3 numbers as an example. I choose 1, 3, and 5. I think same example as last time. We want a peak. So a peak is only going to be done with these 3 numbers if the 5 is in the middle. So the 1 is here and the 3 is here, right? The way they described a peak is that the middle number has to be greater than the other 2. But we can also write 5, 3, 1 like that. So for each of these 56, there's going to be actually 2 arrangements. 1 arrangement, 2 arrangements. So 56 times 2 is the total number, and that's 112. Right? That's the total number of scenarios in terms of the number of peaks. But there's more to this. That's just part of the calculation. The second part of the calculation involves the fact that, remember, you got 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. If you put those 3 numbers here, great. But you have to also fill out those guys. Right? So that's very important. So let's figure out, how can we do this? 1, 2, 3, 4, 5, 6, 7, 8. I can put the peak here. Another way is if I put it here, these 3 guys. Another way, well, you guys get the point, right? I can put it here. Another way is if I put it, those 3, and then finally, how many is there here? I can put it these 3, and then the last one, of course, would be the last 3, like that. So that's 1, 2, 3, 4, 5, 6. So I've got 6 different ways of doing this. Yeah, 6 different ways of doing this. Okay, great. But then what about these other numbers here? Great, I put my, what is it called, peak? I already forgot, local peak. I put my local peak here, right? This is my local peak. But then I also have to fill in these numbers. Okay, no problem. A local peak involves 3 numbers, right? So from the 8 numbers, I chose 3. That means I have 5 left. So I have 5 choices to go here. Then I have 4 choices to go here, 3 choices, 2 choices, and 1. Then I have to multiply them all. So that's basically 5 factorial, which is what? What's 5 factorial? 120? Yeah. Okay, so now let's put it all together. So I've got 6 scenarios, and for each scenario, I've got 120 combinations. So that's 720. And then for each of these, I've got 112 different possible ways of doing that. So grand total will be that 112 times that 720. and that is 80640. So this is actually what represents the total peaks, and that is the number that you would put over here, 80640. And then when you make this calculation, it's just 2. And that's the answer to this question, the average number of local peaks.